With this setup, we are going to have a look at the first effect involving electricity and magnetism. This is a magnetic compass, and what you see inside, the moving part, that needle, is actually a magnet, and when not disturbed, it always points in north-south direction, aligning itself in Earth's magnetic field. This magnetic compass will be disturbed from its natural alignment in north-south direction by presence of another magnetic field. Look at that. I just brought a powerful magnet near it and it got disturbed from its natural position, and it will be also disturbed by another magnetic material like this. This is an iron screw. Iron is ferromagnetic material, and here in this experiment we are going to use this property of the magnetic needle to detect a magnetic field around it. This is a copper wire. Copper is not a ferromagnetic material and it has no effect on that magnetic needle. And what we will do is we'll keep this wire parallel to the magnetic needle and pass current through it and watch its effect on the magnetic needle. I've already connected one end of the wire to the battery. Let me connect the other end and watch what effect it has on the magnetic needle. Look at that. The magnetic needle deflects from its natural north-south alignment, clearly indicating a magnetic field is being produced whenever there is current in the wire. This experiment was first performed in 1821 by Hans Christian Oersted, and he established that electric current produces magnetic field. Fact number 1 involving electricity and magnetism. Electric current produces magnetic field. I will invert this wire, place it like this, and pass current again and watch the deflection. This time the deflection is in opposite direction. Look at that. So direction of magnetic field produced by this wire depends on the direction of the current in the wire. So this is the first fact involving electricity and magnetism. The electric current in this wire produces a magnetic field around the wire all along its length. Electric current in the wire is flow of electrons, charged particles. Electrons are negatively charged particles. So we can generalize the statement, moving charge produces magnetic field. And with this setup, we are going to have a look at the second effect involving electricity and magnetism. This is a coil of 300 tons of insulated copper wire. This type of wire is used in winding of motors and transformers. 4 powerful magnets put together to make even more powerful magnet. Current indicating instrument called galvanometer. This does not read current in amperes. It just indicates the presence of current. That pointer, which is currently at 0 reading in the center, will deflect whenever there is current in that coil. Coil is connected to this galvanometer. We're going to use this to detect the current and also to detect the direction of the current. Right now, the magnet is not moving with respect to the coil, but watch what happens when I start moving the magnet with respect to the coil. Left to right, any which way, any direction, up, down, sideways. As long as magnet is moving, the galvanometer is showing there is current in the coil. When I stop moving the magnet, there is no current in the coil. This effect was first studied in 1831 by Michael Faraday, 10 years after Hans Christian Oersted's experiment, and he discovered the opposite phenomena. Changing magnetic field induces current in the conductor placed in that magnetic field. Amazing. So the first effect is electric current produces magnetic field, and the second effect is changing magnetic field produces current. Michael Faraday called this effect electromagnetic induction. He studied this in detail and formulated 2 laws of electromagnetic induction. Faraday's first law is very simple. It just states whenever magnetic field associated with a conductor changes, current is induced in that conductor, like this. Faraday's second law is also easy to understand. Watch the speed of motion of the magnet and the deflection of the needle in the galvanometer. When I move this magnet slowly, you see some deflection. When I move the magnet fast, watch the deflection, it's huge. Slow if I move the magnet slow, lesser deflection. If I move it fast, more deflection. So his second law simply states that amount of current that is induced in the conductor is directly proportional to rate of change of magnetic field. Slower the rate of change, lesser the current, higher the rate of change, more is the current. Faraday's second law. There is one more effect involving electromagnetic induction, and we know it as Lenz's law. What Lenz's law states is the direction of induced current is such that it will produce a magnetic field that will oppose the change that is producing it. What Lenz's law means in this case is the current is induced in this coil due to the motion of the magnet. And watch, the needle in the galvanometer deflects in two opposite directions depending on the direction of the motion of the magnet. When I lift the magnet, the deflection of the pointer in the galvanometer is on the left and then on the right, left, right, left, right. Now, this induced current of the coil will produce its own magnetic field, and direction of that magnetic field will oppose the motion of this. What it means is if I try to lift this magnet, the magnetic field of coil will try to pull it down, and when I try to put this down, the magnetic field of the coil will try to push it up, opposing the change that is producing it. I can actually feel the pull of the coil on this magnet as I try to lift it, and I can feel the push of that magnetic field when I try to put the magnet down. Lenz's law. Magnetic field due to induced current will oppose the change that is producing it.